sir.
Yeah.
Shall we start, sir?
Yeah, ma'am. We'll
Yeah.
start.
Good afternoon to one and all present here. Silence is a soul's way of gathering strength. Let us begin today's proceeding with a brief moment of silent prayer. Thank you. Respected resource person, esteemed faculty participants, and my dear research scholars. It is my pleasure to extend a warm welcome to day 3 of our 7-day faculty development program on models to manuscripts, structural equation modeling for high impact publications organized by the Department of Professional Accounting and Finance, Kristu Jayanti, deemed to be University, Bengaluru. The second day of faculty development program proved to be a profoundly enriching, laying a robust conceptual foundation in SEN. Our distinguished research person, Dr. Ramesh Babu, from the Department of Psychology, Central University of Karnataka, guided us with the exceptional clarity and depth, setting the stage for more advanced exploration. As we step into day 3, we continue this journey of academic rigor with renewed commitment to learning. Now, we are privileged to have Ramesh Babu with us once again to lead today's session on measurement models and confirmatory factory analysis, a crucial step towards mastering empirical research and high-impact publication standards. We welcome you, sir, for the third day of FDP.
Thank you, ma'am.
Without further delay, I now respectfully invite our esteemed resource person to take over and lead us in this beautiful session. Over to you, sir.
Thank you, ma'am. So let me share my screen. We'll start with where we have left yesterday. Yesterday, for unfortunate, reason, electricity issues, I couldn't, further continue. Remember yesterday we have, I have introduced about this path analysis model, how to draw. So today we will start from that point onwards, like, how to analyze the data, how to, get the, output. So here I'm sharing my screen because I simultaneously use my PowerPoint as well as the Amos software. So this is the model yesterday we have drawn. Hopefully you all have learned how to draw this model using the path diagram using the 4 important keys. So the first one is we have used this draw observed variables rectangular, because since we are using the path analysis, we are using the rectangulars in order to show that these are all observed variables. So we have 5 observed variables we drawn with using this draw observed variable icon. Then we also have used this this single-headed arrow in order to show that the effect of one variable on the other or path. All right. Then also we have used this double-headed arrow in order to showcase that these two are having an interrelationship. Then we have used this icon, particularly unique variable or unique variance. So when I entered this, I have typed this using this object properties. When I clicked this, I was able to add all those names to these variables. So this is what I think yesterday at the end of our lecture before the electricity went, this is where I stopped. So now once you have this particular picture or path diagram drawn, what exactly you wanted to do, then you can click on this particular icon called select data. All right, when you click this icon, and you will have this data files option window. So here you can click on this file name, right? Then whichever folder you have, this will come. So since I already selected this path in gram or path analysis, so then you click on OK, which means that your data had been selected. So once your data was selected, the next thing that you can do is go to the analysis properties next to the select data icon. Select this analysis properties. So this is how the window looks. The first thing is you need to click on this estimation. I think the moment when you open the analysis properties, the estimation, the first one will be there. Make sure that you have a click on maximum likelihood method. All right. So once you have this maximum likelihood method, once you select it, then in the down, for the purpose of computing fit measures with incomplete data, you need to select this fit the saturated as well as and the independence models. I'll explain these, what is the meaning of saturated and independence model in a couple of minutes. Then once you select that, go to the output. So what is the output that I'm looking here? So here you need to select that under the output. You can ignore numerical bias, right? Then you go to the output and make sure that you have selected this minimization history. And there is also tick mark for the standardized estimates and also tick mark on squared multiple correlations. And you can also click on this indirect, direct, and total effects, right? So usually when you select indirect, direct, and total effects, especially when you wanted to do mediation moderation, all right, it works better with the bootstrap approach. All right. So in order to do that, I think when you click on the bootstrap approach, since I have already entered the values, usually the values by default would have been 200, 100, 500. Since I'm using the Amos 31, by default it gave me 200, but I made bootstrapping 2000. It recreates 2000 times data, bootstrap it. So then you can also click on this bias corrected confidence intervals and make sure that you have this confidence interval 95. I think by default it will be 90. 90 will be there. So make sure that you have 95 class interval, confidence interval. Then you can click on this, close it. So once you close this, you can go on this. The next one, calculate estimates. The moment when you calculate estimate, this is how it comes. All right. So remember, immediately you have these values. All right. So this value, the intercorrelation between TBC and attitude was 0.67. And this shows that 0.51, this shows that 0.81. But remember, these are values are actually covariations, which means that you can say that unstandardized values, it's not that standardized. What we are mostly interested in here is the standardized estimates, right? Not in the unstandardized estimates. So because of that, you can, when you click on the standardized estimates, right? When you show unstandardized estimates, earlier it was standardized. When you click on the initially, it will give the unstandardized estimates, meaning covariances between the variables, right? What we are interested in basically the standardized estimates, because we wanted to see the path coefficient or the regression coefficient among the variables. So when you click on this standardized, you can see that here now 47.62 as an unstandardized coefficient. The relationship between attitude and intent was only 0.44, but when I standardize, it has come 0.81 and 0.067, and this is how the standardized path coefficient comes. Now it is very easy to get these values if you are not done any mistake while selecting the options, and it is very easy for you to have these values. But the real challenge here is, what is that I am looking for it? So what does it mean of having these values, right? The interpretation is the most challenging task. In order to interpret it, so you need to have certain indices. So for example, here you can see this is path analysis. Before I explain that, I want you to teach some basics, where you wanted to look at. So assessing model fit is basically depends on four important parameters. So where you look for first chi-square values, and also you have something called an absolute fit indices, and you also have incremental fit indices and other measures. So now we learn about these things, because once we learn properly, because even tomorrow when we do the measurement model, right, the confirmatory factor analysis, we need not to repeat these things. I expect all of you to just have concentration, especially on these chi-square and absolute fit indices. What does it mean, and how we can interpret these values? Because no matter which structural equation modeling you are doing, whether you are doing saturated model, measurement model, or path analysis, so your interpretation is based on these parameters like chi-square, absolute fit indices. So now let me explain the idea of chi-square here when it comes to the structural equation modeling. In this, when I say structural equation modeling, here we are trying to explain the relationship between a set of variables, because we have five set of variables here, like observed variables, and there are two other unobserved variables in the form of error variant, error variables, like measurement error variables, where we drawn to our dependent variables, intent and behavior. So here, what you are going to do here in this, while looking at the relationship between a set of variables, here you have a two competing approaches. The one thing is you have a very complex model which explains everything perfectly, and also you will have a simpler and more elegant model which explains the relationships almost similar to complex model, but with a fewer pieces. So here, exactly what does this chi-square test does in this context is, it helps us to decide whether the simpler model is good enough, or if it was fit. This is what we are going to do it. So this is what the chi-square test let us know, that because we are having a complex model, or you can call it as a saturated model, and we also have a simpler model. So basically the chi-square value help us to decide the simpler model, whether this simpler model is good enough, or whether it has a bad or worse fit. So here there are two important models which I'm talking about it. When I say complex model, which you can also call it as just identified model, or you can also call it as a full model or a saturated model, right? So several textbooks or several paper authors will mention several things, but mostly the researchers use either just identified model or a saturated model. So as I mentioned earlier, this is the most complex model possible in the structural equation modeling. Because why it is more complex? It uses all the available information, meaning all the covariances between the variables, every combination of, with each other variable, to estimate its parameters. So for this reason, we can say it has a direct path from every variable to every other variable in your path diagram. So you can use a simple analogy. It's like connecting every single dot on a page with every line in your paper. And you can say that is a perfect, but because if you every time you are connecting every single dot to every line in your page, it looks like a messy map, right? So that is why we call it as a complex model. So here in this model, we expect that, or we assume that chi-square will always be 0. You know why? Because it uses all the information to create this model. It perfectly reproduces the data it was built from, because it has no room for any error, because you have make sure that, like you have every variable to every other variable in your data set as a there is a path. So we have not left anything, right? That's the reason there is no possibility that there is an error, right? So in that reason, for this reason, we expect that the chi-square value will be a 0. But this is not most interesting part, the other part. So let me show you how this just identified model or a saturated model looks like. Because remember, when you look at the earlier picture, so for example, when I draw what exactly I wanted to draw, I have this picture. There are five independent variable and two dependent variables. I wanted to see that what is this path coefficients, right? But when I actually connecting using the uh, saturated model or a complex model, this is how it looks, because I'm trying to have connection between every variable to every other variable in your data set. If you just count these arrows, there are 15 arrows which will come. Means there are 15 different, path coefficients we are looking into it. As I mentioned here, the most important thing is chi-square. Like, by looking at the chi-square value, what we are trying to do is whether the over-identified model or a reduced model, which is the second model, where you call it as a simpler or theoretically interesting model. Because the model which I draw in the beginning today, what I call it is a theoretically interesting model, because based on the data, what data we are using, we are trying to test this theory of plant behavior, right? So that model is based on this theoretical model. So what happens in the over identified or a reduced model, or you can call it as a simpler model, you delete some paths from the just identified model or a saturated model, because you have a hypothesis here, because you wanted to test your hypothesis that they are not needed, or they are not, we don't want any of those paths because we have certain hypothesis. So that's the reason we say that the coefficient, we assume that there will be a zero. For instance, like, using the earlier analogy, you look at this messy map that you draw in your notebook, and say that I think these five lines are unnecessary to tell the story. So when you have that idea that these five lines are unnecessary, probably you erase them. And when you erase them, you create a kind of a more interpretable map, right? So this is what exactly you do in the over identified model or a reduced model. Here, when you delete certain paths, your chi-square value will be greater than zero, because there is a possibility that we have left certain paths. By removing these paths, the model is no longer a perfect representation like in your saturated model, but there is now a misfit between what your simpler model predicts and what the actual data looks like, right? So when you're looking at the chi-square, this is what exactly you are trying to do. So for example, the non-significant chi-square, like, in this particular data set, we have chi-square of 0.847. I'll just show, where you can see this 0.847. Let us go back to this values, all right? Then after that, right, here you have a calculate estimate size. You have this view text or save the current form, right? Or object properties. Now, what you wanted to do is click on this object properties. Sorry, uh, analysis prop. Where is that? Yeah, view text option. I hope it's visible. One person can confirm. Hello, am I audible? Madam, can anybody respond? Yeah,
Yes,
thank
sir.
you, thank you. Okay, sorry for glitch once again. Straight away, I'll take you through there, like, wherever we stop. Right. I was explaining this, right? Did I share my document? 1 second, let me check. I think I have not shared. Yeah. Is it visible now?
No, sir.
The screen is not visible. The chi-square.
Yes, sir.
Yeah. Okay. Fine. Thank you. So here, I mentioned that the non-significant chi-square in our data, like where can I find this? So for example, for this, you have to go to the output, right? You have these options, right? Amos output. See, when you go to the notes for model, we'll be go through all this, but let us first go to the notes for model. Here you can see that the computation of degrees of freedom by default model, there is a number of distinct sample moments 15 and number of distinct parameters to be estimated 30. So the degrees of freedom is 2. But what we are most interested here is this chi-square value. Look at this chi-square value. We had chi-square of 0.847. This is what I am referring here, right? In our data set, the non-significant chi-square of 0.847. Remember, we assumed that the chi-square will be 0, right? In the saturated model. In the over-identified or reduced model, we said that it will be more than 0. So the non-significant of chi-square in our data indicates that the fit between our over-identified model and the data is not significantly worse than the fit between the just identified model and the data. So in order to understand this whole two lines, it will be little difficult. It's like hypothesis testing. So for that, I have this analogy, right? Read once again. This 0.847 indicates that the fit between our over-identified model, right, and the data is not significantly worse than the fit between the just identified model and the data. So in order to get more from this, imagine you are running a horse race between two models. One thing is your simpler theoretical model, that is what we call it as a over-identified model, and a perfect but useless model, that is just identified model. So imagine these two are two horses, right? When you are running this, a non-significant chi-square, usually typically p greater than 0.05, is like saying my simpler horse or my simpler model did not lose the race by statistically significant margin. It is so close that we can't definitely say that simpler model is worse. Imagine when you are running, right? You and other person is running. Imagine you are a simpler model and the other person is a saturated model. So when you are too close to that person, like, we tend to say that, right? I did not lose the race by statistically significant margin. I was so close, right? So I'm not worse than the other model, right? So we say that it is so close because it is so close that we can't definitely say that the simpler model is worse. Therefore, what we do here is we fail to reject the null hypothesis that the simpler model fits as well as the perfect model. So this can be taken as an evidence that our simpler model is good parsimonious representation of the data, right? So this is what you can imply. But the chi-square has a limitation here because the chi-square statistics is sensitive to the sample size. Imagine if you had a larger sample sizes, the chi-square test will almost always will be significant, where you find the chi-square is equal to, p is equal less than 0.05, leading for you to reject the model, even if it is an excellent representation of the real world relationships. So because of this, researchers, or most of the researchers, rarely rely on the chi-square test alone, especially when you have a larger sample sizes. All right. So here, the true goal of modeling, like, to either measurement model or, path analysis, is to specify a set of paths that can accurately recreate the original relationships or covariances in the data. So here, in this sense, we can say a non-significant result, when you have a correlate chi-square is greater than 0, you can say it is nice, but a significant result is not a death sentence for a model, because if the sample is large and the other fit indices are excellent, so we cannot just go and say that, because I was not able to, you know I was not able to use this or reject or accept my null hypothesis based on the chi-square. That's not the end of the world when we are actually doing the sum analysis, either path analysis or a confirmatory factor analysis. For that, we are supposed to use the other parameters, especially the model fit summary. So the model fit summary looks like this, right? So for example, there will be a default model, saturated model, and independence model. Where you can see this model fit summary, go back to your Amos output. You can click on this model fit, right? So if you see the model fit, I hope you can all see the first table only. I have given this CMIN table, where you have NPAR, CMIN, degrees of freedom, and P values, and the CAMN divided by the degrees of freedom value. What is this values basically indicates? Like, if you see our saturated model, our independence model is statistically significant because it is less than 0.05 level. So let us see theoretically what does it mean. So what does it mean here? The NPAR is, denoted as, or, the full form is number of parameters in the model. So for example, here you have three different models: the model default model, saturated model, and independence model. The default model, because it uses the degrees of freedom n minus 2, it will come 13, right? Degrees of freedom. So whereas the saturated model, as I showed earlier, because it has a path from every variable to other variable, you have total number of parameters in the model 15. Whereas the independence model, this is what our simpler model, because based on our hypothesis, I have removed, I thought that there are paths that are unnecessary for me. So I have only wanted to see 5 different paths. So in the saturated model, there are 15 parameters, meaning 5 variances, one for each variable, and there are 10 path coefficients. Whereas our tested model, which are 13 parameters, we drop 2 paths using the degrees of freedom. Whereas the independence model, where all the paths have been deleted, I wanted to know only the 5 parameters which I initially drawn, right? So this is what this table talks about. Now, about the NPR. Now, if you look at the other columns, CMIN, CMIN, and the degrees of freedom, especially CAMN. So CMIN is a chi-square statistic value here. So here, this chi-square statistics compares your tested model and the independence model to the saturated model, right? You can see CIMN is the same value where we have found 0.847 in the earlier occasion. Here you can see the same value for your default model. Where the saturated model, because it's a perfect model, you have equivalent to 0. Whereas the independence model, you have 134.142. So the other important factor, like, parameter, you need to look into this chi-square divided by the degrees of freedom. So what is this? the chi-square divided by the degrees of freedom is basically the relative chi-square, or which is an index of how much fit of the data to model has been reduced by dropping one or more parts. Because we have dropped so many and we have kept only 5, it's this relative chi-square value will give such an indication. All right. So other than these values, there are other absolute fit indices. So what are those absolute fit indices? You have this root mean square residual, you have the goodness of fit index, you also have the adjusted goodness of fit index, and also parsimony goodness of fit index. So these are all come under the absolute fit indices. So you can see here this particular data here. All right, the fit indices, yeah, this particular second table where you can see this RMF, GFI, AZFI, and PZFI. So what is this theoretically meaning? All right. So here the root mean square residual, meaning RMO, is an index of the amount by which the estimated model or estimated variance by in your model and covariances differ from this observed variances and the covariances. So here we expect that, we assume that, or the smaller the value, smaller the RMR value will be the better, because the larger the value, it indicates the worst fit between your model into the saturated model, right? The reduced model to the saturated model. The other value where you can see the GFI, here you can see the GFI value is 0.994, right, in your default model or the tested model. You can see that here the goodness of fit index, what does it tell us? It tells us what proportion of the variance in the sample variance and covariance matrix is accounted for by the overall model. So here the researchers says, or the standard is the GFI or the goodness of fit index should exceed 0.9 for a good model. There are other researchers are also who propose that this can be 0.95, which indicates a better model. But conventionally, we can say that any value which is greater than GFI 0.9 is a good model. For the saturated model, like, if your model, your reduced model is an indicative of saturated model, it will be a perfect, right? So this is what we were able to see here. Almost our values are near perfect, right? So see here, because our GFI value is almost 0.99, right? Which is almost near to the 1, right? Meaning our reduced model is closely, going with the saturated model. So here, other than this GFI, you also have these adjusted goodness of fit indices, where you can see this adjusted fitness. This is GFI is 0.994. When you adjusted this GFI value, it has come as 0.96, meaning 9.957. So what is this 0.957 indicates? The adjusted goodness of fit index is an alternative to the GFI, in which the value of the index is adjusted for the number of parameters in this model. So here, the fewer the number of parameters in the model relative to the number of data points. So for example, here variances and covariances in the sample variance to the covariance matrix. So here, the closer the AZFI will be the GFI, right? Because you see that GFI is 0.994. Our AZFI also will be very closer, because we had almost 0.96 value. The other one, the last column in that particular second picture, you had this parsimony goodness of fit index, which we call it as a PZFI, which is an index is adjusted to reward sample models, and it penalizes models in which few paths have been deleted. So note that for our data, the PZFI is larger for the independence model than our tested model. So you can see here, because it rewards and penalizes, in this particular model, the PGFI is larger for our independence model. See here, the independence model PGFI is 0.314, whereas the default model is 0.133. All right. So these indices or the fit indices is showing that our model is very close to the saturated model. Other than these PGFI or absolute fit indices, you also have something called comparative fit indices or incremental fit indices. So you have this NFI, CFI, these are all comes under the incremental comparative fit indices. So these goodness of fit indices basically compare our model to the independence model rather than to the saturated model. So your default model or your tested model will be compared to the independence model, not to the saturated model. So one such comparative fit indices is NFI. I think you can see here the NFI, the baseline comparisons where you had NFI, RFI, IFI, and TLI. And here, if you go back here, the 0.994 base comparison, right? You have the TLI as almost 1.046. So let us see that what does it mean. So the NFI, the full form normed fit index, basically ranges from 0 to 1. With higher the value indicates a better fit. So here in our case, we have NFI of 9.994. So we had a better fit. So the NFI is simply the difference between the two models chi-squares, the divided by the chi-square for the independence model. For example, if you look at our data, that is 134.14 minus 0.847, then divided by this 134.142. This is what the value of NFI. So for example, here you go back and check the values, right? You had this 134.47 minus 1.47 divided by this independence value will give you this NFI value, right? Which is 0.994. So the this is about the NFI value. Other than this, the most important one also you have this comparative fit indices. The comparative fit index uses a similar approach as NFI and is said to be a good index for use even with the small sample. Imagine when you had a smaller samples, right? We tend to go with the comparative fit index. But if you read any articles which are published using either path analysis or confirmatory factor analysis, mostly the people will give all these indices, right? NFI, TFI, CFI, everything. So the CFI basically ranges from 0 to 1, like the NFI, and 0.95 or higher indicates a good fit. So the current conventions, mostly the certain researchers says that statisticians especially, if the CFI is more than 0.95 is good, but conventionally, if you read any textbooks, the standard textbooks, they also mentions that even CFI more than 0.9 is also good. It's not a bad, but you should not have less than 0.9, right? The other one, other incremental value, which is the comparative fit indices, which we call it as Tucker-Lewis index, typically ranges from 0 to 1 value, with the higher the value indicating a better fit. Values below 0.90 often indicates a poor fit. You can see this as well. Our TLI value, right, is more than 9, 0.146. All right. And similarly, you have this parsimony adjusted measures and other things, because though you have all those things, not everything will be reported. But what is mostly reported is this RMSE value, right? So you can see this comes under the other measures. So what is this other measures? Root mean square error of approximation, right? This particular value, the RMSE estimates a lack of fit compared to your saturated model. Basically, if your RMSE value is less than 0.5, it indicates the good fit. And even if you had value of 0.08, then you can say less adequate. But if you have values point less than 0.5, it indicates the good. You can see here in our data set, the model data set, your RMSE is 0.000, meaning it's a well fit value using that 5 paths. So this is what basically about the path analysis. Remember, these models, like these fit indices, like whatever we discussed, right, will be applicable for the CFA model, like whether you are using measurement model or a saturated model. Like when tomorrow I will do this CFA, like I'll not be going to explain this. Simply you can look at those values and see that whether your model is fit or not fit, whether you had a better fit or a worse fit, right? So then after this, completing this the path analysis, now let us move on to the measurement model, which is a confirmatory factor analysis. Basically, we do confirmatory factor analysis once we establish something, like especially in the tool development, right? Where you have developed a tool, when you wanted to establish that, you ensure that your measures are valid, right? We use this measurement model. So what do you mean by this measurement model? A measurement model basically describes how well your observed variables or indicators measure the invisible theoretical concepts or factors or the latent factors. Basically, how well your observed variables or indicators measure these latent factors. That is what this measurement model is all about. So in confirmatory factor analysis, we test a specific hypothesized measurement model. So this measurement model basically defines exactly which indicators are supposed to measure which latent variables and how strongly these, right, are related. Basically, looking at the factor loadings, we'll be able to see that, how strongly these, indicator variables are related to the latent factor. Here, in confirmatory factor analysis, our goal is to confirm, like our hypothesized model, or reject whether the proposed relationship between these observed indicators and the latent factors fit the actual data that we have collected, right? Any method, you can also give this particular definition. You can say any method of testing a priori hypothesis, because the moment when you say confirmatory factor analysis or a measurement model, we are supposed to have a priori hypothesis in order to test the effect of a particular relationship among a set of observed and latent variables, observed and unobserved variables. So for example, one difference, if you would have already have certain idea about exploratory factor analysis, because in the exploratory factor analysis, all measured variables are examined, like in relation to all underlying latent variables. But when it comes to the confirmatory factor analysis, it imposes certain theoretical restrictions so that the observed measures relate to some latent factor but not the other factors, which means that when you have certain variables, measured variables, certain items, you know that this particular item comes under this particular dimension, right? Not with other dimensions. So here the CFA specifically deals with this measurement models, which basically quantifies the relationship between your observed observations, where you observed during your research, and the underlying theoretical construct which you thought or which you think that these observed variables are measuring a broader latent variable or the factors. So the CFA requires, as I mentioned earlier, you need to pre-specify all aspects of this particular model, right? Thus, the researcher must have a firm priori sense based on either the past evidence, meaning if you don't have any theory or theoretical framework, probably you can come up with this a priori or hypothesis based on the prior empirical research articles, right? Or the number of factors that you think that exist in your data based on your exploratory factor analysis, as well as which indicators are related to which factor or so forth. You can use any of the logic, but the idea is you must have drawn certain paths based on your hypothesized model in order to optimally perform this confirmatory factor analysis. So here, there are different purposes we use the CFI, right? Confirmatory factor analysis. It is not a single purpose we use it. There are four different major purposes. The first thing is, if I wanted to evaluate a psychometric evaluation of the newly developed tool, right, where I have established my exploratory factor analysis, just I wanted to confirm, like, those factors are retaining, right, using a different sample, right? When I develop a new test or a new instrument or a new measure. And I can also use the confirmatory factor analysis where I wanted to validate my tool, or find the construct validation, and also test any method effects are there, and also to test the measurement invariance, right? So here, let us try to finish the theoretical aspects today, so we can straight away start tomorrow performing this confirmatory factor analysis. So here, the first thing is psychometric evaluation of test. So CFA, this is the first purpose, right? So the CFA is used during your scale development process, because you wanted to examine what is the latent structure of a test instrument. Example, for example, a questionnaire which you recently developed. In this context, where you wanted to develop a psychometric evaluation, the CFA is used to verify the number of underlying dimensions of the instrument, or number of factors that comes, and what are the pattern of interfactor relationships. Because it is not that we are looking at path analysis, we are looking at the confirmatory factor. It looks that which are the observed variables or manifested variables fall under a particular factors or latent variables, and it also looks for, is there any inter relationship between your latent variables, right? So the CFA basically assists in determining how a test should be scored. Whether is it that you wanted to have a composite score, or whether you wanted to have a dimension score. So for example, you have personality tools in psychology, right? So there you have individual scores. You can't say there is something called a total personality, right? Similarly, self-esteem, there is a total score. But there are other variables where you can have this dimension wise scores, because the total score and the dimension scores are very different from one tool to another tool. So here, when the latent structure, like meaning when you have a multifactorial, like tool which you have developed involving more than two factors, the pattern of factor loadings supported by the CFA indicates how a test may be scored using these subscales. Like, so for example, there are tools. You have this, Neo FFI, right? A personality factor inventory by McCosta and Mecker. You had 5 question model. So you know that how to indicate, how to analyze the scores, or how to interpret the scores, because there are 5 dimensions in it, right? So that is the number of factors, which is indicative of the number of the subscales, and the pattern of item factor relationships indicates how the subscale should be scored. That's the reason we use the confirmatory factor analysis when you have the multifactorial tools. Here, the depending on the results, CFA may also support the use of total scores, which composite of all item scores. So Rosenberg self-esteem, right? Or if you have a particular job satisfaction, right? Or psychological well-being, right? You have certain times you can use both the subscales, both the dimension-wise scores as well as the total scores. Sometimes you can only use the total scores. Sometimes you can only use the dimension scores. So it can support the use of either total scores, or in addition to your subscale scores, which is composite of all your subset of scores. Additionally, CFA can also be used to estimate the scale reliability, right, of the test instrument in a manner which avoids the problems of traditional methods. Usually, you need not to do a CFA in order to run the reliability. You can simply do the Cronbach alpha, right, outside the CFA. But actually, CFA also provides the reliability, which is much better version of, using the Cronbach alpha, because fundamentally Cronbach alpha has certain limitations, right? Because it looks for inter-item correlations basically, right? For that, if you are using confirmatory factor analysis in order to run the reliability, I think it will give you a better, picture of about the reliability. Additional to this psychometric evaluation of the test, you can also use the CFA in order to have the construct validation, or validating your constructs, right? So the constructs are basically unobserved and theoretical, or you can call it as a factors or latent variables. Although these constructs are unobserved, there is an often related theory which describes how these constructs should be related to one another, right? Because though we know that these are unobserved, so for example, when we measured intelligence, we cannot directly observe what is your intelligence. We have certain ways to figure it out what could be your intelligence based on the relative scores of from different populations, different samples. So here, the basically what happens, though we are aware that these are unobserved, there is an often a theory that talks about how these constructs can be related. So according to this Cronbach and Mean, one of their papers in 1995, they said that the cross construct validity basically refers the examination of a measure of an attribute or a construct that is not operationally defined or directly measured. Because in measured variables, we define operationally. What do you mean by this variable? But when it comes to the construct validity, we are not doing it, right? The construct that is not operationally defined or directly measured. So that is what we wanted to find out the construct validity. Under the construct validity, there are two types. One thing, you need to establish both convergent validity as well as the discriminant validity. So what is the difference between convergent and discriminant validity? The convergent validity basically indicated by evidence that different indicators of theoretically similar or overlapping constructs should be strongly interrelated. Imagine I'm developing today a new intelligence tool, right? If I wanted to establish a convergent validity, because there are n number of intelligence tools that are already there in the market, in the usage. So now I should be able to find an intercorrelation between already existing tool to the current tool. When measures of the same concept are highly correlated, then you can say that there is a evidence for your convergent validity, right? For example, if you are interested in job satisfaction, right, we may look for a strong relationship between the data which you gathered using a self-reported job satisfaction, right? And also you can also measure not from self-reported measures. You can ask their co-worker ratings. You can ask about how satisfied your colleague in this job, right? So the co-workers rating of an employee's level of job satisfaction. If you find out these two, highly correlated, then you can establish that there is a convergent validity, right? So whereas the second type of construct validity, which is a discriminant validity, the discriminant validity is indicated by result showing that the indicators of theoretically distinct constructs are not highly intercorrelated, meaning there are low correlations among these concepts. For example, when examining construct validity, it is essential to note that the same correlation between two latent variables can be either good or bad depending on the relationship that we expect, right? So if theory suggests that job satisfaction and burnout are distinct constructs, right? Then based on my theory, because I assume that these two are different constructs, I expect to find out a low to moderate correlation between these two constructs, because I know job satisfaction is nothing to do with the burnout. In this case, I only assume that there would be a low to moderate correlations when I actually do it, right? If we find a correlation of like minus 0.36, right, between these two variables, job satisfaction and the burnout, then we have an evidence of discriminant validity, because this is what I have predicted, because this is what I assumed, because I assumed that these two are very different. However, if I find a correlation of point minus 0.87, then I cannot have an evidence of discriminant validity because the correlations are too high, right? So, which means that these two are, because I'm looking at, I assume that there is a lack of correlation, like these two are very different, but my data shows that there is a high negative correlation. So, this is what indication. If I assume, if the theory had suggested the job satisfaction and burnout measure the same construct, then I would be looking for a convergent validity, because I see that these two are related constructs. Because assuming we have a different methods for measuring these two constructs, because you cannot measure using the same self-report questions. You should look for other ways of doing it, like collecting the data. Then we would interpret a correlation of the same minus 0.36, right, as not supporting the convergent validity, because the correlation is very low, or I can say moderate correlation. However, when I assume these two are correlated, a correlation of 0.87, right, minus 0.87 would suggest a good convergent validity, right? This is what the most important aspect that we should understand, because a lot of time, people tend to, misinterpret the construct validity and the discriminant validity. So if you can see within this broad discussion of construct validity, the confirmatory factor analysis plays a limited at very crucial role. Specifically, the CFA can be used to examine the structural validity, that you can say factorial validity, such as whether a particular construct is unidimensional or a multidimensional. Then how these constructs are interrelated, whether this particular construct or any sub-constructs or sub-dimensions you had, how these are actually interrelated. The CFA can be used to examine latent variable structure of an instrument during the scale development process. Actually, when you develop a tool, like, I use this because I use the first two purposes. One is psychometric evaluation, because I wanted to see the whether reliability is there. I can also establish this, convergent validity and discriminant validity. For example, if an instrument is designed to have a 40 items which are divided into 4 different factors, I had 10 items in each, then the CFA can be used to test whether the items are related to the hypothesized latent variables as expected. Because as a researcher, when I start writing the items based on my theoretical knowledge, or the evidences or a theory, when I start writing as a researcher, I thought, okay, this item would be coming under this, like, this dimension, all right? But this can only be checked when actually you collect the data. So this is what the CFA as actually does. Though you have, there are 4 dimensions under this scale, like, you have your own thought of, latent variables, but this hypothesized relationship, can be indicative of whether these items are related to the what you have hypothesized or what you have expected, which indicates the factorial validity. If, for example, sometimes you may have the prior work available, meaning you had done exploratory factor analysis, you might have published initial validation using the exploratory factor analysis, then the CFA can be used to verify the pattern of factors and loadings that were found, whether I can confirm. I have published 2 tools. One is informal caregiver burden, and as well as this academic cheating. All right. So both the papers, I have not done confirmatory factor analysis. Of course, the academic cheating paper, that actually we are done with confirmatory factor analysis, that is currently under the process of getting published. So the CFA can be used to determine how an instrument should be scored, whether a single total score is appropriate or a set of scores is more suitable, can also be determined looking at the construct validation, right? These are the first two important purposes why we use the confirmatory factor analysis or a measurement model. The third one, we also use the confirmatory factor analysis to test the method effects. What do you mean by method effects? The method effects simply refer to any relationship among variables or items that result from the measurement approach used. Because you might have used this self-report. You know that you are giving certain number of questions and you are asking and you know how to respond. Nowadays there are a lot of method effects because people when you send a data, collect the data using Google form, imagine that if you are reading every question to fill 40 questions, at least it takes 30 to 40 seconds. You know that how much time it takes, but there are people who submit it in just 2 3 minutes because that there is random filling. So if there is such effects because you have collected the self report, you don't know whether the person has read the question or not, because if it is a self report, I might have my social desirability. I may not given my responses honestly, right? More broadly speaking, method effects may also include the response bias effects such as social desirability and other things. So the CFA can also be used testing is there any method effects. The common method effects are a widespread problem in research as they can create a correlation between the two measures, making it difficult to determine whether an observed correlation is the result of a true relationship or the result of shared methodological approach. Because you have had the shared methodological approach for you collecting the data, you are not sure whether there is a that actual relationship is the identified relationship is an actual relationship or it has come from any error. So there are different methods you need to use. For example, self-report versus observation, or self-report. Earlier, I was talking about job satisfaction, right? Self-report, as well as you can ask the individual how happy you are, how satisfied you are, or you can also ask their colleagues, their ratings about how satisfied your colleague is. Or in order to avoid this method effects, you can also use the positively or negatively worded items, because sometimes people without reading the items they may also respond. So this wording may also result in lower than the expected correlation between the construct, or it can also suggest that there are two or more constructs when there is actually one. For example, when measures include both negatively and positively worded items, data analysis may suggest that the presence of two factors when actually there is only one expected this one. Because you have certain examples in psychological data, especially this Rosenberg self-esteem. Initially, when the Rosenberg self-esteem developed scale was developed, this is a perfect example of this problem, right? For example, this Rosenberg self-esteem includes both positively worded items as well as the negatively worded items. So when initially the Rosenberg has conducted an exploratory factor analysis in the beginning of his career, consistently yielded that there are two self-esteems, right? Because there is positive self-esteem, then there is a negative self-esteem, right? So because all those positively worded items comes together and finding out under one factor, all the negatively worded items have come under the one particular label called the negative self-esteem. But however, there was no strong conceptual basis for the two-factor solution, because then further CFA, when he does after this exploratory factor analysis, he found that there is only one factor model allowing for a correlated residuals. That is what we say the method effects provided a better fitting model than the earlier two factor models. So that's the reason we use whenever you have this kind of problems, method effects problems. I think better you can use the confirmatory factor analysis in order to test. So here the conceptualization of the concept of self-esteem, because meaning the underlying theory was very much critical component of testing this one factor solution. Because the Rosenberg himself has given this theory, or some XYZ has given a theory. If a theory is talking about a particular unifactor, like theory, then why your data is showing in exploratory factor analysis, then you need to check that, like whole data set, how exactly you have measured it. So the method effects can exist in any measure, and one of the evidences of CFA is that it can be used to test for these effects, whereas some other types of data analysis cannot. So for example, no other way of finding this method effects unless this uh, confirmatory factor analysis. Finally, the final purpose we use the confirmatory factor analysis is the testing the measurement invariance. What is this measurement invariance? Measurement invariance refers to testing how well the models generalize across groups over a period of time. So, for example, you might have a collected data using a particular group of people, or a particular section of people, or say culture, or a race, or a caste, or a particular gender. So it tests that how well this model which you have developed can be generalized across the other groups. If a test is intended to be administered, say for example a heterogeneous population, it should be established that its measurement properties are equivalent to in subgroups of that population, because it's a heterogeneous population, not a homogeneous population. So irrespective of their gender, race, you should be able to find the suitability for you to use this particular scale. So here a test is said to be based by said to be biased when some of its items do not measure the underlying construct comparably across your groups. So this test bias can be very much serious, because such as in such situations where a given score on a cognitive ability or a job aptitude test does not represent the same true level of your ability, all right, or an aptitude in male and female respondents equally. So this can be measured, like using the measurement invariance. You can also state this problem in another way. The test is biased against women if for a given level of true intelligence, men tend to score higher in several IQ units, higher than the women, which means that the test is biased towards the women, because there is a test biases, because these test biases very much serious, because the test itself is having a gender bias. So these questions can be addressed in CFA by multiple group solutions and multiple indicators or multiple causes, like MIC models, because we have a limited time, and we'll not be able to cover all those things. If you are more interested, at the end of, I think tomorrow, I'll be sharing few reference lists where you can go through those reference lists if you are more interested to learn about how to do this multi-group solutions and multiple indicators. All right. And for instance, if you are doing a multiple groups confirmatory factor analysis solution, the measurement model is estimated simultaneously in various subgroups. So for example, you can estimate this measurement model or measurement invariance for both men and women at the same time. So other restrictions are also placed on the multiple group solutions to determine what is the equivalence of the measurement model across your groups. For instance, the factorial loadings are equivalent to the magnitude of the relationship between the test items as well as the underlying construct. Is the same for men and women. If at all you establish there is no the testing biases or gender biases or any biases that your test has got, right? This is what the measurement invariance. So then tomorrow I would like to start with conducting CFA normos, and also you see that how based on this confirmatory factor analysis works, how can we actually use the modification indices. So I would like to spend around 1.5 hour to 2 hours time. So I would like to complete the whole, so whatever I planned as per part of this video by tomorrow. So thank you so much for your patient listening. If you have any queries, probably I'll try to answer your queries here for another probably 5-6 minutes.
Dear participants, we kindly request you to share any queries in the chat box or unmute and ask directly.
Okay, sir.
I think no more queries.
I hope they understood. Yeah.
On behalf of Department of Professional Accounting and Finance, I extend my sincere gratitude to Dr. Ramesh Babu T, Department of Psychology, Central University of Karnataka, for an insightful and enriching FDP session on models to manuscripts, structural equation modeling for high impact publications. Sir, your expertise and clarity have significantly enriched our understanding. Thank you so much, sir.
Thank you, sir.
I also wish to thank all participants from Kazazan University and other institutions for your active engagement and meaningful contributions. And we look forward to your presence in tomorrow's session as we continue our collaborative pursuit of academic and research excellence. Thank you once again and have a pleasant evening.
Thank you, sir.
Dear participants, thank you, sir. Dear participants, kindly complete the FTP feedback form that has been shared in the chat box. Thank you once again.
Thank you, sir. Amit sir, you can end the meeting.
Yeah, ma'am.
Participants, you can leave the meeting.